For ages, man gazing with wonderment at the... But only by 1961 had rocket power developed to a point where he could actually... Now man faced a serious question. How could he survive in this virtually unknown environment? To fully understand the problem, artificial satellites explored the conditions of space which man would encounter, while ground laboratories investigated the problems of man's survival in space. We shall study some of these and their solutions. We begin with air. Like all matter, air is composed of atoms and molecules shown here as spheres. Those nearer the ground are pressed together by the weight of the trillions above them, progressively denser and heavier. A column of air, 1 inch square, and the height of Earth's atmosphere weighs about 15 pounds. This is why air normally exerts a pressure of 15 pounds on every square inch of our bodies at sea level. As we go higher, there are fewer and fewer air particles above us. Hence, the weight and pressure of air decreases. 5 miles up, air pressure is only 5 pounds per square inch. The air pressure inside this testing chamber quickly drops below 5 pounds per square inch when the membrane is broken. Note how the liquid in the beaker bubbles. For at low air pressure, gases dissolved in a liquid are released as bubbles. Without protection, the man's body fluids would bubble. Because air in the lungs is also sucked out, this would be fatal. Another danger in a space vehicle is the accumulation of carbon dioxide, the gas exhaled in breathing. The man becomes groggy when 4% of the air is composed of carbon dioxide. Then, unconscious. A higher percentage would cause death. Radiation of atomic particles is perhaps the greatest danger to man in space. Solar flares near active sunspots produce such atomic particles. Others originate outside the solar system. As symbolized here, they move at tremendous speed. When these primary rays strike atoms or molecules of air, both shatter, producing fragments, as shown by this analysis. The fragments, called secondary rays, hit other atoms and molecules. Only a few rays finally reach the ground. For this reason, radiation at ground level is much less severe than the massive radiation in outer space. Whenever primary rays hit the walls of a space vehicle, symbolized by this metal sheet, they break into secondary rays that shower the spaceman inside. Equipment surrounding him can provide only minor protection. Solar activity is continually observed. Therefore, it is always possible to call off a flight if solar activity is unusually high. Weight is another major problem in space travel. On Earth, the weight of a body is caused by the Earth's gravity. When we weigh an object, we measure the force of Earth's gravity on it. The normal force of gravity at the Earth's surface is 1 gravity, or 1 G. Besides gravity, the force of inertia can affect weight. Newton's law states that matter at rest tends to remain at rest. This means that matter resists acceleration. Before takeoff, the rocket and the manned capsule on its top are at rest. This model spaceman will show what happens to the live passenger inside the capsule. When the rocket takes off, it accelerates violently. The man's body resists this acceleration, and the force of this resistance, added to the force of normal gravity, increases his weight. Note the pressure he exerts on the membrane. As the rocket continues to accelerate, the man's weight continues to increase and may reach 9 times the pull of Earth's gravity, or 9 Gs. In orbital flight, when jetting stops, acceleration stops, and all weight disappears. If not strapped down, the spaceman would float freely. For the forward-outward pull created by the speed of the vehicle exactly equals the pull of Earth's gravity. The opposing pulls neutralize each other, causing all weight to disappear. But when the vehicle re-enters the atmosphere, air resistance slows it down, and this deceleration causes the man's weight to return. Newton's law concerning inertia, namely that matter in motion tends to continue in motion, explains why the block continues to move after the vehicle is stopped. So too, the man's body tends to speed on as the vehicle decelerates and pushes against the vehicle with about 10 Gs of force. Equipment such as this rocket sled revealed the main problem resulting from violent acceleration and deceleration, which is that blood made heavier by multiple Gs would rupture blood vessels just as the liquid breaks this balloon. Weightlessness, the opposite of multi-Gs, is another problem, one not well understood. These floating men are in an airplane, flying a curved path whose outward pull equals the inward pull of gravity, thus simulating a capsule in orbit. So far, we have studied the main problems of man's survival in space. Let's begin with a space suit and see how these problems were solved for early space flight. Oxygen coming from a storage tank and pressured at 5 pounds per square inch circulates throughout the suit to cool the spaceman's body and then passes into the helmet for breathing. Exhaled air next leaves the helmet, passing first through chemicals which absorb carbon dioxide, then through a cooler which absorbs heat and condenses water vapor. The air can then be used again. Earlier, we observed the effect of multi-Gs on a liquid inside a balloon. When the balloon is strongly supported, it does not burst. The space suit applies this principle. As Gs increase, flexible tubing along the fingers, limbs, and torso is tightly inflated with air to support the blood vessels. Further protection from multi-Gs comes from a contour couch molded to the spaceman's body. It places his heart and brain at the same level. This prevents blackouts caused by blood moving away from the brain, or hemorrhages caused by blood rushing into it. American space capsule designed to re-enter the atmosphere without burning up. Small meteorites are vaporized by the heat generated by compressing the air in front of them at their tremendous speeds. To avoid this danger, the vehicle re-enters the atmosphere with the wide end leading, so that air resistance will slow it down. The dark portion covering the wide end of this capsule is a heat shield. The heat generated by air resistance burns the shield instead of the vehicle. A historic flight is about to begin. We shall see how the solutions to various spaceflight problems work out in actual practice. The worldwide radio system is ready. Vital information on the functioning of the spaceman's body will be automatically transmitted to the radio receivers on Earth. This data and his personal report on the flight will help advance space technology. The vast preparations are now complete. The towering launching rocket majestically takes off and soars spaceward, bearing a man inside the tiny capsule at its tip. As the rocket accelerates, the man's weight increases. About 3 minutes later and 100 miles up, the rocket is in orbit. It aims the capsule toward a predetermined orbital path. The space vehicle jets free. When the jetting ends, weightlessness begins. The vehicle is in orbit at about 17,000 miles per hour. A camera in the vehicle films the spaceman. He swings the vehicle around so that the heat shield faces forward, ready to return at any moment. Below gleams the Earth, where millions anxiously await news of his flight. Moving through the silent darkness of outer space, every moment of the capsule is followed by the network of radio stations. When the retro rockets are fired, orbiting ends. These rockets reduce the capsule's speed and push it downward. The launching rocket, which has been following the vehicle, now passes overhead. The launching rocket will re-enter the Earth's atmosphere in about a week and burn up. The burned-out rockets are cast off to clear the heat shield, which is then positioned to re-enter the atmosphere head-on. Small jets rotate the capsule to disperse air compressed by the wide shield. In the thin upper air, speed decreases gradually. But 15 minutes later, the air thickens perceptibly. The heat shield becomes white-hot, burning at 3,000 degrees Fahrenheit. Speed decreases from 15,000 miles an hour to 7,500 in just 1 minute. Here, about 25 miles up, the spaceman's weight increases to more than 10 Gs. From this point down, Gs and heat fall off, and the spaceman prepares for a landing. Now the chutes take over the capsule's descent and land it safely in the ocean. It can float indefinitely until picked up by a helicopter, which carries the man and vehicle to a waiting ship and final safety. Space flights such as these are a tribute to the heroism of men like the Russians Yuri Gagarin and German Titov, and the Americans Alan Shepard, Virgil Grissom, and John Glenn, and a triumph for the centuries of scientific research in mathematics, astronomy, and physics, in chemistry and biology, which made possible these first steps into space.